Okay, yeah, it's recording. Okay, so this is our tutorial 2. Okay, maybe before that, just briefly analyze the question in this tutorial. Okay, so this is the question to be discussed. Okay, I have briefly looked at the tutorial questions. So basically, we can categorize into several types. Okay, so first we have this type number 1. So they were asking you guys to construct a particular random variable. So that is only one question. So that is question 1. And after that, so there's a second type. So which asking you to verify whether is a random variable or not. Okay. So that means a function is given corresponding to a given sample space and a given sigma field, and after that you need to verify whether that is a random variables or not. So there are several questions on here. Question 2, 3, 4. Okay, which fall into these categories. And also the next one. So that's a sigma field. Okay, generated by X. Okay, so that is only one question, question 5. So this is the so-called the sigma field generated by X. I think this is a quite straightforward one. Okay, so and number 4, type 4. So which is a question 6 to 7. Okay, so that's like that. So which is ask you to find this, which is regarding to the distribution functions. Okay, so question 6 and question 7. Oh, I think up to question 6 up to question 8, 6, 8, 7, 8. Okay. So next one B. Okay, so this one, so you need to verify something whether that is a probability density function or probability mass functions or not. So that's only one question, but several type. Question 9. And so next we have so this one is the, how should I say, this is or maybe we say we knew random variable from a given random variable. Okay, so we have a given random variable, and then we use some kind of the Borel function to define a new random variable, and after that we ask several questions on it. So this is a question 10 and question 11. So basically these are the questions that which will cover in this tutorial here. All right, so according to here, then we shall look at question 3A. Why is that so? Okay, and after that, question 7B. Why is this? Okay, so okay, so this is actually also fall into here, and 9, mainly the last 3 questions. Okay, I think question 7B, which is also fall into the part 2 here. Okay. So in this case, so let's briefly recall the definition for this random variable. Okay. Okay. First of all, let's say as usual, we have a probability space omega a sigma field F, and we have a probability. We have a given discrete entity. Okay, so it's known. This is a sample space. This is the sigma field, which means the collection of all the events and the probability which define on all the events here. Okay. And next, once we have a probability space over here, then we said that if we have a function x which define on omega to r. So we said that this real value function x is a random variable if and only if okay, maybe one by one. Okay, A. So this is a random variable if and only if this condition holds. That is x less or equals to b belongs to f for any real number b. Okay, so we just verify the pre-image for x. Sorry, the pre-image for this interval under the mapping f. See whether it is an event in the here or not. Okay, so this is for general case. So this is for general setting. Okay. I think maybe I should put it over here. So this is for a general setting. So in particular, so if we have a discrete case when x is discrete. So what does it mean? So meaning that image of x is a discrete set. So in this case, then we can say that x is a random variable. So we have a relatively simple criterion to test whether it is a random variable or not. That is, this is the one. X is a random variable if and only if x. So here is less than. So we can say this is equals to maybe k belongs to here. Or image k of x. So this is for the discrete case. So when x is a discrete case, so what we need to do is we just need to verify each of the discrete value for x. So in general, so we have to verify this one usually will be an interval. This is the thing that we need to get it. Okay. Okay, so then let's look at a question. I think maybe I need to write down. What are the questions? 3A, 7B. Three A, 5A, 7B. All right. Okay, let's look at the questions. 3A. Do I have the solutions? So let's go 3A. So here's the questions. Okay, a coin is toasted once, so omega is ht. X of h is 1, h of t is 0. Okay, so that means in this case, x represent whether the outcome is hit or not. Okay, so determine whether x is a random variable respect to each of the following sigma field. Okay, So this is the questions. So let's go to this. Okay, question 3. Okay, first of all, we know this omega is h or t. So as usual, okay, so all right, so f is not specific, okay, so we only have this. So and also given x of h is equals to 1 and x of t is equals to 0. So I think it's clear this is a discrete case. Okay, and this is this case, and I think it's clear. So the images of x, there are only 2 of them, which is 0 and 1 only. So that means you just have to test this criterion for 0 and 1. All right, so then what we can see, this is the case. Now we can look at it. We have this, then I think it's clear. X equals to 1, so because h is 1, so that is h, and the pre-image for 0 will be t, because there's only one possibility here. So we have these 2. Okay, now what we need to do is, so since this is the case, right, so what we need to do is, so we just need to verify whether these 2 h, okay, maybe I would say these 2. What do you mean by these 2? Means this and this. Okay, this set and this set is are even or not. Okay, so which is actually based on the this criterion here. So we just need to test for it. Okay, we just need to. Okay, now we have 2 parts. So for part A and B, part A, right? Okay, so for part A, so we have this. The first sigma field consists of only 2 elements here, empty set and this. Okay, now you can see this one does not belong to here. Neither one of them belongs to here. Okay, so in this case, then you can see that this H, which is not an element in here. Okay, or actually you can make another, or you can claim that this is not an element in here. Either one. Okay, because of this doesn't belong to here, so x is not a random variable for this case. Okay, so it's not difficult. Basically, we just using this criterion to check for it. So you have no comment with B, right? So I suppose B, you can make it. Okay, for B, because of the sigma field is the power set, so that's why all function must be random variable. Yeah. So just to let you know, for B, the sigma field is the power set. So for this, all function must be random variable. So we don't have to worry about it. So when we consider this power set, so it must be random variable for any kind of the functions. So that's why we don't have to worry about it for this case. Okay, so just a remark for you. So only part A, so we need to do the verifications for it. So the next questions, question 5A. So actually, A and B are the same. In fact, we can say question 5B is a special case for. Okay. Okay. In fact, you can say that B is a special case for A. So in general, the answer will be like this. I just write the answer. Okay. So in general, so question 5. So in general, so for x is equals to 1a. So the indicator function with this set A. Okay, so this is the case here. So I just write down the answer, and after that, I explain why the answer looks like that. Okay, in somewhere else. Okay, so for x equals to this, then the answer will be sigma x will be the sigma field generated by x will be the empty set A, the complement of A, and this. So how to get this? Okay, so just some remark for you. So because this is actually a simple functions, right? So you can see if we have this x equals to 0 is equals to this, and x equals to 1 is equals to a. So that means we have two functions. Two disjoint partitions. So from here you can see A and AC form disjoint partition. So when we have this case, so you refer to the lecture note, so then we can see automatically it will be the sigma field will be like this. Okay, the sigma field generated by S will be the empty set and A in complement and together with their union A union AX. I think that's it. So that's why you can get this. The last one must be our omega. Yeah, just like this. So for question, actually, for the next question will be exactly the same. So maybe I can just put it over here for question 5B, right? So that means what we can do is A will be, I think put a whole correct complete information. So in this case, omega is the closed set 0, the unit closed set 0 to 1, and A is the set 0 to 0.3. Okay, so in this case, then we must have the complement of A must be 0.3 to 1. Okay, so what you need to do is you just plug into here, then you will get the answers. Okay, so that's why in this case, then the answer will be sigma field will be generated by X will be the empty set 0 to 0.3 A and 0.3 to 1, and together with the omega. So I think this is straightforward, huh? Okay, so next we go to question 7. I think it's the same questions. Is this the questions? Question 7B. Okay, this one. Okay, again, it's the same kind of question. We want to test whether X is a random variables or not. Okay, first of all, let's look at this. Okay, a die is rolls twice. Huh? So exhibit a suitable probability space omega script f p for this random experiment. So I think this is quite straightforward. This is actually a discrete case. So when this is discrete, so then we can imply X is also discrete. Okay. So the reason is the domain is a discrete, then the images cannot be more than a domain. So it must be discrete as well. So X is a discrete random variable. So that's why we also go back to this criterion. Where is it? Okay, so that means we are still talking about this criterion. Okay. So what we need to do is we just need to verify this conditions. So that's why what we need to do is we just need to identify all the images for our X in this case. All right. Okay, so let's go back to our question, sir. So X, oh sorry, I think it's typo. I think forget about this. Let X denote the sum of two numbers appears in each outcome. Just define this one is a random variable. Okay, I think B is okay because of okay, maybe we start from the beginning. We start from beginning. I want to establish a suitable probability space for this random experiment. Okay, maybe what you can do is, so we can take, in this case, omega will be equals to small omega, so which consists of two elements, omega 1, omega 2. So whereby omega 1 running from 1 up to 6, same as omega 2 running from 1 up to 6. So from here, you can see, I think it's clearly the number of elements inside here must be 36. Cardinality for this sample space will be 36. Okay, so let's begin with part A. I think, so this is our omega. This is our sample space. So as usual, we follow the standard scheme. So this is a discrete one. So what we can do is we just simply take, if without any specific reason, so we just take the power set to be the sigma field. Okay, so this is number 2. And number 3, we need to define the probability. So what we can do is we just define this. P omega equals to, so the cardinality is 36, 1 over 36. For all omega belongs to this. So then what we can do is we can construct, so the probability like this, follow our standard scheme. P of A will be, we summating all the elements inside A. P omega. So this is part A. So actually, so now we let X be the sum of the two numbers. So that means X will be equals to omega 1 plus omega 2. So X omega will be the sum of them, omega 1 plus omega 2. So from here, I think this is quite straightforward. So the images of X will be, so 2, 3, 4, 5, 6, 7 until 12. Okay. This is actually doesn't really matter because of our sigma field is the power set. So that's why it must be a sigma field. Sorry, it's a random error. So you can see it. Okay. So this is a power set. So must be belongs to here. For any k running from 2 up to 12. Okay. So once we have this, then we can make a conclusion. Hence, X is a random variable. In fact, when the sigma field is the power set, like I said, all function must be a random variable. But anyway, I think it's not difficult to identify this, right? So maybe I'll just give, for example, X equals to 10. X equals to 10 will be equals to, how to get 10, by the way? 1, 2, 3, 4, 6, 5, 5, and 6, 4, right? Example, so this is the one. Okay, if you want to get another one, X equals to 7 will be 2, 5, 3, 4, 4, 3, 5, 2. I think that's it, right? Okay, so and so on. So this is how you can identify the subset. But actually, it doesn't matter. This is not important anymore because of if we follow the standard scheme. So we're going to take the sigma field to be the power set of omega. So that's why automatically all these subset must be belongs to the sigma field. Okay, so that's why it doesn't really matter. We don't have to verify it. So we need this when we do question C. So nobody raised question C, so I suppose you can make it. So that's why I can stop it here.
Sorry, doctor.
Yeah.
Can we add on question D?
Sorry?
Question D.
Question
Part
D.
Yeah.
For which one?
For this question.
For these questions.
Yeah.
What is question D, by the way? I limit. Okay, maybe it's better I follow here instead of reading my papers. Wow, find the distribution. What is my answer? You answer? Oh, no answer. Okay, it's too troublesome. You guys go and verify on yourself. Is it all right? Okay, maybe I will just do the first few steps and then you guys go and complete it on yourself. Okay. All right, so the problem is the images of X is from 2 up to 12. So that means I have to do the calculation for 11 times. So that will be a little bit troublesome. Okay, so I just do the first few and the remaining you guys go and do it. All right. Okay, just one by one. So part D. So in order to do part D, so we need to calculate the probability. So you guys go and do it one by one. Okay. So first of all, the probability for X equals to 2 will be how many of them? How to get 2? Okay, maybe again, I think I just do some of the images. Okay, maybe I will just do the first few and the remaining you guys go and do it on yourself, okay? So for example, first, when X is 2, how to get 2? How many? Okay, 1, 1, only one element, right? How to get 3? So that is 1, 2, 2, 1. And 4 will be 1, 3. So 2, 2, yeah, 3, 1. Huh? Okay, and so on. So I think no point for me to carry on. So this is standard things. Okay. Okay, from here then you guys can calculate the probability. So Px equals to 2 will be because it's only one element, so 1 over 36. So P of x equals 3. So there are 2 of them, right? So 2 over 36. px equals to 4 will be 1, 2, 3, so 3 over 36, and so on. And finally, I think the last one will be 6, 6, right? So 1 over 36. So altogether, 11 of them. Okay, so 5, 5, 1. Okay, yeah, 11 of them. So then you will get all these things, right? Okay, I think from here, then you can get the value. You again, as I said, you guys go and complete the thing on yourself. So that means you have altogether 11 expressions. I think more than that. Okay, so that means you can see t. So you will get 0 when t is less than 2. Right? So and when I think I move it over here. So 0 when t is less than 2, less than 2. Okay, and 2 to infinity, negative infinity. So next, when t is from 2 to 3, including 2, okay, excluding 3, so that means that will be 1 over 36 because of that's only one. So the next one, when 3 to 4, so that means you must do 3. So that is, you have this one plus this one. So you're going to have 3 over 36. And when it comes to the next one, 4 to 5. So that means will be you have to sum up all of them. 1 plus 2 plus 3. So that's why it have to be 6 over 36. Okay, you go on. Okay. So that means you have another one, 5 to 6, 6 to 7, blah, 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 until the very last one. That is 11 to 12. I think when 12 onward, you will get 1. So the second last should be 35 over 36. Okay, I think you can refer back to what you have learned in the undergraduate study. Okay, so this is the thing for it. Okay, so this is the standard scheme to compute the distribution function for discrete random variables. All right. Okay, I think should be okay. Okay, I think maybe the solution is too long, so that's why I skip it. But it is actually a standard question. Huh? Okay, so let's carry on to question 9. Okay, so determine whether each of the following function is a probability density functions or not. Okay, when we talk about this probability density function, so that means we want to identify whether it represents absolute continuous distribution. Okay, so then we refer back to our criterion here. So before we continue, so look at again notes. So we have a function. F is a density function, or it's defined. Okay, maybe we put in this way. You put in this way. So F have to fulfill 2 conditions. Okay, so the first conditions, first of all, F must be always non-negative. Okay, it cannot be a negative number. And the condition 2, if we integrate over R, so it is what? Okay, so when f satisfy A and B, so then f is a PDF. So that means f can define a proper probability. So basically, we just need to verify condition A and condition B. So just like that. So I think the first one actually is always very clear. The only one that we need to verify will be the second one. Right. So let's look at here. I think forget about this. So I think this is quite clear. All these f always greater than 0, right? For all of them. So this one always greater than 0, this one greater than 0, this one greater than 0. So that means the first condition all pass. So all of them greater than 0. So we only need to verify the second condition. So what is the answer? I think I should have the answer. Okay, yeah. So so the detail will be the standard calculation. So I'm not going to do it over here. So you guys go and verify it on yourself, right? Okay. Okay, the first one, f is this. Yes, first of all, f is non-negative, and we can verify this is equal to 1. The reason is from negative infinity to 0, the value is 0. So that's why we just need to integrate from 0 to infinity. So this is 1. Yes, answer is yes. Okay, just like that. So what you need to do is you just need to use what you call it, the integration by parts, the standard calculus technique to verify it. So the next one also the same. Yes, because we can verify fx is non-negative, and if we integrate f over the real numbers r, then the value is 1. Again, it's a standard calculus calculation, so I leave it to you. And part C also the same. No. Okay, part C you can see, because if you integrate these functions over R, the value will be square root of pi. How to get square root? Why? Why this is square root of pi? Okay, but anyway, let's forget about it first. Okay, most importantly will be this. If we integrate this function from negative infinity to positive infinity, the value is not 1, then it is not a PDF, just like that. And part D, yeah, part D is actually looks like the density function for standard normal distributions. Okay, so except you're supposed to be a square root 2 over here, so that's why the value is not 1. So that's why this is not a density function. Oh, okay. I think I got it. So C is actually looks like a gamma function. Okay, maybe this one. You refer to a gamma distribution. Okay. So this one is actually sort of like this gamma distribution. So this one sort of like a normal distribution, standard one. Okay, maybe I'll put it over here. So again, when x is a gamma, alpha lambda, so the PDF fx is given by, my gosh, I can't remember this already. How is it? Gamma functions. Okay, so I think lambda x alpha minus 1 e minus lambda, so over gamma alpha lambda. Yeah. So when x is a random variable following a gamma distributions, so the PDF will be given like this. Okay. So if we want to get back to our pattern, so what do we have? Square of x. Okay, square of x. So that means I think maybe we can put it in a proper way. So that will be lambda alpha x alpha minus 1 e minus lambda t over gamma alpha. So how to get okay, so that means if we take lambda is half, right? Yeah, negative half. Lambda is half. Okay, alpha is half. Okay, so if you take this, then we can see our fx is equals to half power of half. I think x power of minus half, then e minus x over 2 over gamma half. Yeah, I think it's supposed to be in this form, 1 over gamma half will be square of pi 1 over square of 2x e minus x squared. Yeah. Okay. So you can see for gamma distributions, lambda is half, alpha is half. Okay. So the density function is supposed to be in this form. So if you compare with the questions, I think it's clear, right? That the pi missing. Okay, you can make comparison. So the pi missing here. So that's why in question C, this function is not a PDF. So I think this is clear.
Doctor, is this a prerequisite?
What do you mean
Is this like a prerequisite knowledge?
I suppose so, because I always you guys should have taken a statistic course in your undergraduate class, right?
I don't know about my peers, but I've not seen gamma.
Okay.
Hola, right? That's it.
Okay.
I'm just asking because, like, in the context of exams and tests, I think we need to make it clear what's our expected prerequisite if this kind of questions.
Okay, I would expect you guys are familiar with, at least you guys from. Okay, I will give you a formula tables. Okay, formula tables for those known distributions. Okay, what is a prerequisite? So I would assume you aware of things like so-called normal distributions. Okay, you should be aware what is a normal distributions, and or you might not able to recall its formula, but at least you're aware there's such a thing so-called normal distribution and something so-called Poisson distribution and gamma distribution, etc. Okay. Yeah, at least you should aware of this kind of standard distributions. Okay. Gamma, or maybe I'm not going maybe a chi-square Poisson gamma. I think that's it, right? So I'm not going to I don't think I'm going to touch the T distributions, but at least you know there's something so-called distribution and F distributions and verbal and so on, right? Etc. Okay. All the standard non-distributions. And also I will provide a formula sheet for you guys. Okay, so at least you can always refer to that formula. Those are standard formula for those standard distribution like normal, Poisson, and so on. Okay. All right. So this is standard things. Of course, and those are like that binomial as well. Okay. Right. I think once you're aware of the criterion and you're aware of the pattern of the function, then this thing should be quite clear. Huh? Okay. Next, we go to number 10. Actually, what's the problem with question 10? It should be quite straightforward. Okay, let's look at here. As usual, P will stand for the probability of success, okay, or fail. Depends on what event you want to consider. Okay, let's say P is a probability of success. Okay, X is a random variable with probability mass function. Okay, for example, if you look at here, I think you guys should know, right? So this is actually the mass function for a binomial distributions. Okay, but doesn't matter, it's given. Okay, find the probability mass function for each of the following random variables. So A and B. So I think question 10 should be quite easy because of X is a discrete case, so Y is also discrete. Okay, I can move to here. So question 9. Okay, so given Px equals to K is equals to NC X. Okay, I'm using X. NCX, Px, and Qn minus X, right? When X is 0, 1, 2, up to n. So again, as usual, so this one, you can see X is actually a binomial distributions with a probability of success and n-tra, yeah? So this is K. So this is a discrete case, okay, A. Y is X squared. So when Y is X squared, X is run from here, right? Then automatically you can see the image for Y will be 0, square root of 1, square root of 2. Am I right? No, it's not square root. X 1 square, 2 square, 1, 4, 9, and so on up to n square. So that means you just need to consider all these values on it. So then you can see Py equals to small y. That means this is a y. So that is x squared equals to y, or P of x equals to y. So what you need to do is you just need to replace your x with y. Square of y. Okay. So that means this is just equals to nc square of y. P of square of y, and then q n minus square of y. So the value of y will be like what I say. For those that didn't mention, that will be 0. And then equals to 0 for otherwise. Okay. So for B will be also the same. I'm talking about this is e square z. So just for your information, you can check it out. So that means this is e power of 0. So e1, e square of 2, and so on. E square of n. So what you can do, you can just follow this sort of calculations. So P of z is equals to small z is equals to and because of x is positive, right? So this is 1, 1. So we can see this is how should I say x is your square of x is non-z. And if you square both sides, so p of x is ln z square. So again, what you need to do is you just need to substitute into the formula. So then you can see this is NC. So this is supposed to be your x. Okay. So again, this is for your z is the value E0 up to e power of n and 0 otherwise. Okay. So I think so for next one, so the answer was given for question 11. So maybe we can directly refer to the answer. So this is the questions. Okay. We look at this x is a random variable with this probability density function. Okay, I think if you remember, you still can remember. Is it Cauchy? Yeah, I think this is Cauchy distributions, right? If I'm not mistaken. Okay. So this is a density function for Cauchy distributions. Okay. Okay. So again, we consider y equals to x squared. So x is from negative infinity to positive infinity. Okay. I think okay. Next, want to find the probability density functions. Okay. What we can do is we can identify the distribution function first. So f y will be this. So I think this is the definitions, right? The first line should be okay, just the definitions. And y is x squared, so we just substitute inside. So I think from here to here should be okay, right? X squared less than y, so then x must be in between minus square of y and square of y. So I think here to here is a standard and a metric. Okay, next, this one. So it depends on you whether you want to consider half of it or you consider whole, because you can look at this. Okay, so this function is a symmetric respect to the y-axis, so they look the same. So that's why you can just consider from 0 to square of y and then multiply by 2. Okay, so we have this because of this function is symmetric. Okay, this one because of x is symmetry, or you can say x is even. Okay, x is even, or x is symmetry respect to the y-axis. Okay, so this is because of x of negative of x will be equals to f of x. So when you have this, so you can simplify the integral equation for it. Okay, so the next one, so this is from here to here. So this is the definition for the density functions. So we can have this. Okay, so this is the one. Okay, maybe the next step, if you want to calculate this. Okay, maybe, I think, okay, maybe we can do it this way. So question 11, right? So we have this. So this one out to be 0, fx, x, and dx. Huh? And this one, so we can see this is actually equal to 2. We have a okay, so this is 2, 1 over pi 1 plus x squared dx. And this is the standard integrations. Then you can see this is 2, 1 over pi up tangent of x of y to 0. Okay, so then it turns out to be 2 over pi up tangent of x. Sorry, square of y. So this is your density distribution function. So if you want to find a density function, you just need to differentiate it. So that's why f small y. So that is you just differentiating this respect to y. So you differentiating this, then you will get this straight away. So differentiating this will be 1 over 1 plus y. It's supposed to be the square of it. And then you differentiating this thing, so we're going to have how is it? I think 1 over 2, 1 over square of y. Okay, and this is how you get, I think, the same answer, right? This is how you get this answer. So actually, you don't have to do the integrations. You can actually use a theorem of calculus, fundamental theorem of calculus, you can get it. So that's why this is how to get the answer will be 1 over pi and 1 over 1 plus y and 1 over square of y. Actually, this is a question for a standard undergraduate statistic or probability distribution course. Okay, if you have attended an undergraduate statistic course, so you should have seen this kind of question before. Yeah. Right. So I think this is what we can discuss for our tutorial 2. Okay, just nice. So we spent 1 hour for it. Any other question for this tutorial? No. Okay. Let's up.
I want to ask for number 1B, right? I don't understand the answer actually for number 1B.
Okay, okay, no problem. Number 1B. What is number 1B? 1B. Okay. Okay, about this. Okay, question 1. So we have omega is 1, 2, 3, 4, 5, 6, right? So this is, we know already. So this is 1, 2, 3, 4, 5, 6. Okay. So if we look at B, we are interested on whether the outcome or the phrases that appear on top is an even numbers or not. Okay, so that means we are interested on 2, 4, 6. So that's why what we want to know is how should I say it? Okay, it is sort of like x defined on here. Okay, x is a function defined on this. Right. So we interested on even number of here. So that means we just say x omega is 1. Okay, when omega is even. Because we are interested on whether the outcome is even numbers or not, right? We just define x omega as 1 when omega is even, x omega is 0 when omega is not, means odd. Right, so that means from here, then we have only 2 of them. So x equals 1 will be 2, 4, 6, and x equals 0 will be 1, 3, 5. Okay, so if we define a function that corresponds to each of it, so that means we just define our omega like x like that. X omega is 1 when omega is even. X omega is 0 when omega is odd. So that will be the function that we're going to define. One way for it. Is this the answer? Okay. I'm putting y instead of x. I'm using k instead of omega. So this is the way. Okay, because we are interested whether the output is even or odd or not. So that means we take 1 when the outcome will be even numbers. Right? Okay. So I believe should be okay, right? Then okay, so then we continue to chapter 3. Okay, in chapter 3, this is what we have discussed. Okay, I think we have stopped these 2 formula, right? So we have already discussed. We have 2 formula. This is the formula to compute the density function for x plus y if x, y are independence formula. Independence random variable. So we look at 2 different cases. Case number 1 when they are absolutely continuous. Okay, so we have this formula. The other case will be when they are independence and discrete value. And to be easy, make it easy, we consider x, y are positive. So the formula will be this. So we can use these 2 formula to compute the value like this. Okay, I think this example is a little bit complicated. So I'm not going to go to this. Okay, if you are interested, you can verify it on yourself. Okay, maybe I can look at a special case when x and do I need to go there? Okay, when x and y are standard normal distributions. Okay, so let's look at the case when x and y are standard normal distributions, and I just demonstrate the calculation. Okay, the idea for the calculation, how to get these things. Okay, I just consider the standard case. For x is a standard normal distribution, and y is a standard normal distribution. Okay, make it easy. The calculation are more or less the same, but so which means I consider this is our mu x will be 0 and sigma x will be 1, and mu y will be 0 and sigma y will be 0. So if we use a formula, so that will be this. We integrate fx v minus y and fy y. So we have this. This is true because of xy. So because xy are independent, okay. So then we can separate them. So next we just put in the, because x is a standard normal, y is a standard normal, then we have this. So for x will be 1 over square root of 2. Okay. So in this case, e minus y minus v minus y squared over 2. And here we also have another one, e minus y squared over 2 dy. So this is for our fx, this is for our fy here. So what you can do is we can actually take up all these constant, 1 over square root of 2 here, and 1 over square root of 2 here. So for this, this is a standard integration. So we can have a y squared minus 2 dy plus v squared. And minus, it becomes plus. So that's why we're going to have 2 here. So again, if you recall the standard form for the normal distributions, or normal distribution will be 1 over sigma square root of 2 e minus 1 over 2 x minus mu over sigma squared. Maybe we can say this is y instead of y. So we want to put it in a standard form like this. So we have a 2 over here. So we need to cancel out 2. Or we need to do something about the 2 here. So that is this. So what you can do is you multiply by 1 over half and half. So then you will get like this. E minus y squared minus 2 v over 2 y plus v squared over 2 divided by 2 and this. So which is very much looks like this pattern now. Okay. So actually the remaining are standard calculation. So you just need to complete the square here. So it will be y minus v over 2 square. So if you minus, then you have to you have an additional one, v squared over 4 plus v squared over 2. Okay, now you can see this is already following this standard form. Kind of, okay. So you just look at this part. So this one you can take it out. So minus 1 over 2, then you put it inside. Y minus V over 2. You have half here, right? So you can put a square of half square. And this one, if you can have this is okay. So you look at this this part here. So you have a minus of minus V over 4 plus V squared over 2, and then divided by 2.5. So you can actually cancel off this 2. Okay, so then it end up to be minus V squared over 4. Actually, minus will become plus. And this is what you can have. So that's why you can actually take out this is E positive V squared over 4. Then you have a dy. So this is a constant. You can actually bring it out over here, and you have a half over here, and you want to put a standard form. So you have to put a sigma and sigma here. Okay, so from that's why then you can see this one end up to be 1 over square root of 2. Okay, and okay, this one you can take out. So that is a E V power 4 over 4. Okay, so you have a 1 over square root of 2 pi E minus half of this Y minus V over 2. So if you want, then you can say this is a square root of half square dy. Okay, so you might want to put this thing over here. So that's why you have to put a square root of half over here to represent the sigma. Okay, so you cannot have an extra, so you have to multiply 1 over square root of 2 here. Okay, so you can see this whole thing will end up to be 1. So then this is, then you can get this is remaining is 1 over this. Then this is a E of V power 4 and 1 over square root of 2. And this thing will be 1. Okay, so then you can see this end up to be things answer like that. So 1 over 2 pi multiplying 2 and E minus V squared over 2. So this is the answer. So that's why this is very much looks like the pattern you can see. That's why 1 over 2 pi sigma x squared plus sigma y squared 2 and E minus half V minus half sigma x squared sigma y squared. What is something like this. Okay, I think I put it in a proper way. So because we have taken mu x to be 0, mu y to 0, sigma x to be 1, sigma y to be 1, so that's why it come up to be this value. Okay, again, this is not a hard theory in probability, but just some standard calculation in calculus. Right, so I think in the next one should be quite straightforward. What you need to do is you just need to remember this is the functions. This is the formula. Okay, so this is the formula. Okay, the mass function for x plus y will be like this. Okay, okay, next is given that x is a Poisson with mean lambda, y is a Poisson with mean mu. So I think by the formula you can have this is the formula p of x equals to k. So for Poisson, again, this is another standard distribution. So I will expect you can remember the form. You are familiar with the formula, okay? So the mass function will be e minus lambda because there's this lambda, lambda power of k, and k factorial. Likewise, this is mu. You just need to replace lambda with mu. Okay, and this is n minus k, so that's why you can replace this to be n minus k here. So this is how you can get, sorry, this is a typo. So this one's supposed to be e minus mu, okay. Again, okay, I think maybe I show the detail for the calculations. Let's look at the next example. So example 3.2.5. Okay, so given x is a Poisson with lambda, so which means px equals to k will be e minus lambda k factorial. Okay, and also given y is p mu. So that means py equals to, okay, so maybe y will be e minus mu k and lambda y over y factorial. Okay. So by formula, using the formula, we know p x plus y equals to n can be written as we summating from 1 0. It begins with 0. Px equals to k. Py equals to, okay, so we can see n minus k. So that means you just need to replace this with y into the formula. So that's why then you can have, this is summating. So substituting, so e minus lambda k factorial. So for this one will be e minus mu k n minus k factorial. Okay, just replace this with y. So what can we do? Okay, first of all, we can take out this E minus lambda plus mu, okay? What do we have? This is okay, I think there's a typo over there. Okay, maybe right. So this is a summating k equals 0. Okay, so we have taken out these two. Okay, so these two has been taken out. So the remaining will be this. Okay, so we can put it here. Then we're going to have a lambda k. Then we have a mu n minus k. Okay, we have a k factorial in this. So we have a k factorial n minus k factorial. Right? So it's supposed to be 1 here. So now what we can do is we purposely put in an n factorial here. So to be balanced, so it have to be divided by n factorial over here. Okay, so you have to cancel off, then it came back to the same things, right? Right, so this part, by using the binomial formula, so this is equals to lambda plus mu power of n. So this is by the binomial formula. Okay, so this is the what you can have. Okay, so this is lambda over here. So that's why this thing will end up to be this e minus mu lambda, and then over n factorial lambda plus mu n. Okay, so that is a typo over here. Please make a correction. So this will be n instead of k. Right, so that's this one's supposed to be n, and this one's supposed to be n. Okay. Okay, so this is how we're going to use the formula to work out some calculations over here. Okay, good. 7:30 now. I think as usual, let's take a break for half an hour so you can have your dinner or go for your praying sections, right? This one, stop recording.